This is a large water tank that is open to the air at the top and has a small hole or spigot in the side out of which this spout of water is being ejected. We would like to be able to predict the speed with which this spout of water is exiting the tank, and we can do that by applying Bernoulli's equation and making a few approximations here. So the main one being that when we say the tank is large, what we mean is that the cross-sectional area of the top of the tank here, what we'll call gate one, is so much greater than the cross-sectional area of this tiny hole in the side, which we'll call gate two, that the tank is being drained very, very slowly by this spout. So slowly that we don't notice any change in the water level here in the short time it takes this spout to form. So with that approximation, we then turn to considering the conditions at point one here and point two along some particular imaginary streamline that could, in principle, carry a tiny fluid element from the top of the tank out through that hole in the side. We can apply Bernoulli's equation to point one and point two along such a streamline. We'll need to consider what the pressure is like at point one and at point two. At point one, it should be fairly clear to us that the pressure here, where the water is meeting the air, is equal to the atmospheric pressure, 1 atmosphere of our yellow air here. So the pressure here at one is 1 atmosphere. But at two, let's be very, very specific. Point two is the opening of that hole where the water is contacting the surrounding air here at the side. And so where the air is contacting the water here at the side, at that location, just like here at one, the pressure of the liquid and the pressure of the gas must match where they are in contact. This is essentially Newton's third law for fluids. Two fluids must have the same pressure where they come in contact. In this case, the fluids are the water and the surrounding air. So the pressure here at point two, right at the mouth of that hole, is also 1 atmosphere. The pressure at point one equals the pressure at point two equals atmospheric pressure in this scenario. I want to say a little bit more about that. If you look at the stream of water coming out of your faucet here, there's no surrounding pipe around that water anymore. It's just surrounded by the air. So at all points in this stream of water, the pressure of the liquid has to match the pressure of the air that it is in contact with. So the pressure in this stream of water throughout the whole stream is 1 atmosphere. 1 atmosphere. Now, we do notice the narrowing of the stream as the water speeds up due to the continuity equation. And I've tried to show that here in my drawing as well. See the narrowing of the stream as the water speeds up. That's due to the continuity equation. It's not due to any change in pressure. The pressure everywhere in this stream, the pressure of the water matches the surrounding pressure of the air, 1 atmosphere. That's Newton's third law for fluids. So in general, where water exits a hose or a pipe, right, where it comes out, the water pressure equals the air pressure. And that can be hard to accept. I'm going to say even more about it. Consider this little picture here, where we've got a garden hose, let's say, with water coming out, and we could see the water spilling out of an open hose like this at point two, or we could put a nozzle on that hose to concentrate the flow into this narrower jet there, and then ask, is the water at 4 just outside the nozzle at a higher pressure than the water here at 2 just outside the mouth of the hose? And we probably naively think that this pressure at 4 is higher than at 2. The pressure of this jet, oh, that's a high pressure jet right there. Pressure at 4 higher than at 2. But no, that's not the case. The water here at 4 is in contact with the surrounding air, so it must match the pressure of the surrounding air, 1 atmosphere. Likewise, at 2, this water is in contact with the surrounding air. Its pressure must match the pressure of the air, 1 atmosphere. The water is faster at 4 than at 2. It has a higher speed, because of the continuity equation. Let's say we had the same flow rate Q coming in at 1 and at 3, the same number of gallons per second at 1 and at 3. The difference in speed comes from the narrowing effect of this nozzle. The cross-sectional area here at 3 is wider than the cross-sectional area of the mouth of the nozzle there. So the water has to speed up from 3 to 4 since the cross-sectional area goes down from 3 to 4. So the water does speed up here, unlike at 1 and 2 where the cross-sectional area is the same at 1 and at the mouth, so there's no speeding up of the water. So no doubt the water is faster at 4, but the pressure at 4 equals the pressure at 2, does equal the atmospheric pressure due to Newton's third law. There must be high pressure somewhere here to produce this fast stream of water, and that occurs back here at 3. The higher pressure must be here in order to force the water through that narrowing pipe, speeding it up so it exits at 4. So the high pressure in this picture is at 3, not at 4. Pressure at 4 matches the pressure at 2, matches atmospheric pressure. Back to our water tank then. Let's now use these ideas to determine the speed of the water at point 1 and at point 2. Let's first apply the continuity equation to this streamline of water from 1 to 2. That water passes through gate 1, or like all these streamlines, these 4 streamlines pass through gate 1. Then all 4 of those streamlines pass through gate 2. So we can apply the continuity equation to gate 1 and gate 2 and say that AV at gate 1 has to match AV at gate 2. And then if our tank is very large, so that the cross-sectional area of the hole, gate 2, is much, much smaller than the cross-sectional area at gate 1, that less than means much, much smaller than, then that means that the speed at 2 has to be much, much greater than the speed at 1. In fact, we're going to approximate the speed of the water here at gate 1 as being very nearly 0. The tank is so big that this spout is draining it so slowly that the water level at the top of the tank is dropping at a negligible rate, barely dropping at all. So our speed effectively is 0 here, very nearly 0, certainly negligible compared to the speed at 2, where it comes shooting out of that tiny narrowed hole right there. So continuity equation tells us this, and now let's apply the Bernoulli equation to points 1 and 2 along this particular streamline right here. And the points we were making earlier were that the pressure at 1 matches atmospheric pressure, and the pressure at 2 at the mouth of that hole also matches atmospheric pressure. So those two terms will cancel out. We can subtract them to cancel them, and then let's start rearranging this equation to try and solve for V1 here. So we'll get our 2 gravitational potential energy terms on one side and our 2 kinetic energy terms on the other side. And then notice, now that pressure has canceled out, the density of the water has appeared on every single equation. So we can cancel out, am I going to be able to do that? Cancel out density from all 4 of those terms. Next up, then, I'm going to factor out little g from the left-hand side and factor out the 1/2 on the right-hand side. And here make the approximation that we've got the V2 squared minus V1 squared. So this is the speed at the spout, and here's the speed at the top of the tank. And we've already said that our speed at the top of the tank is much, much less than the speed at the spout. So we are going to neglect that term there, say that that is negligibly small compared to V2. say if like V2 is 1,000 and 1,000 squared and V1 is 1 squared, 1,000 squared minus 1 is still approximately 1,000 squared. Makes a negligible contribution there. So we're going to drop that term according to our large tank approximation. So dropping that term, then it's easy to finish this off. We can finish rearranging to solve for V2, and we get this expression where the speed of the water exiting the tank just depends on the difference in height between the top of the tank and the hole. So if we put in a value for that height, 3 meters, according to our picture here, this is up at a height of 6 meters, and our hole is down at 3 meters here. So the difference in height is a 3-meter difference. That's where our hole is located. Then we can predict the speed at which that water exits the hole. And I'd like you to notice that this expression here, the equation we ended up with, this is the same equation that we would get if we had just dropped, say, a ball from a height of z1, and we're predicting its speed as it fell in free fall by the time it got to a height z2. This equation here is the same result as free fall. So interestingly, the water being ejected from the side of this tank is coming out at the same speed as if we had just dropped that water from height z1 and let it accelerate under the influence of gravity alone, as if pressure had nothing to do with it. So then that's our speed of the water coming out the side at V2. And if we go back to consider V1 from our continuity equation, we must have that V1 equals this ratio of those cross-sectional areas times V2. That's from our continuity equation here. And again, if the size of the hole is tiny compared to the cross-sectional area of that tank, then this value is negligibly small, approximately at 0 there. Okay, so what we've done is exchanged gravitational potential energy for kinetic energy along that streamline. This is point 1 on the streamline. Here's point 2. The pressure at point 1 was equal to the pressure at point 2, atmospheric pressure. We've just changed gravitational potential energy for kinetic energy, much like as if it were a simple free fall problem.